Okay, thank you for the introduction. Thank to the organizers and for all of you to staying so close to lunch. So I will speak about again controllability of quantum systems, in especially for Schrödinger equations, so infinite-dimensional version of quantum systems. I will try to present the details in a couple of slides. So the main equation we have in mind is a bilinear system like this. So we have an Hamiltonian which evolves in an infinite-dimensional Hilbert space, which we call H. And okay, typically the controls which we use will be some bounded, will take value in some bounded set of this Rm. So they are real controls. And then we have different notions of controllability which can be considered in this setting. So we have already spoken of exact controllability. So can we go from any initial state to any final state C1? Can we go approximately, so just close to the final state with arbitrary precision? And then we can also consider the variants of this equation, like the Liouville formulation. And then we try to steer a density operator rho naught to a density operator rho 1. And this we can try to do it exactly or approximately, or we always would like to do it exactly, but there are some abstractions that we have already heard from the previous talk. And then we can also consider up to which extent we can have operator controllability. So really the flow of the, we want to control by U the flow of this kind of equation. So this is any finite flow that we would like to have. So it's a unitary operator on H. And then we want to find control such that the flow associated with this control is exactly or approximately equal to this letter epsilon here. Okay, so what is the goal? So in 2 lines of my talk, the first thing is to substantiate this kind of claim that these kind of systems are in a generic sense. So if I pick it randomly in some sense, the Hamiltonians H naught, the non-controlled Hamiltonian, the controlled Hamiltonians, I get a system which is approximate controllable. So in some class that I will try to describe precisely. And so the first, the middle part of my talk will be about this, give some details about this claim. And then to pass to some stronger notion of controllability, which together with Marco Caponigro, who is co-author of this work which I'm presenting, is we called controllability in projections. So which is a way of measuring, I would say more qualitatively than quantitatively, how approximate controllability works. So approximate controllability can be of different types. So here I try to plot. So this is a 3-dimensional torus. So parallel faces are identified, and then we can have a dense object in this torus, which is typically a line with a slope with an irrational components irrational between them. So this gives a set which is so it's a possible attainable set in this torus, which is dense. So we have this kind of approximate controllability, but we don't have. So if we project this trajectory on this 2-dimensional torus, so we look at the first 2 components of this attainable set, we have again something which is dense here, but not equal to the entire 2-dimensional torus. And what we want to say is that the approximate controllability that we prove for this Schrödinger equation is stronger than this. So we have already the possibility to cover in full flash this two-dimensional torus. So the projections cover well. We can in fact control exactly the occupation levels of finitely many modes, and in fact arbitrarily many but finite modes. Okay, but I will give a more formal definition in some slides. So I start by recalling finite-dimensional results. So we have already seen in Gunther's talk. So I take again the same structure of equation, but now in a finite-dimensional space, so in Cn, and then we have already seen that the important object here is the lift of this equation in the corresponding group, in the group UN. And because of this rule that it was written here, some kind of the attainable set in the group applied to the initial condition psi naught gives the attainable set in the sphere starting from psi naught. Okay, so the important thing here is to understand how this attainable set acts on the unit sphere. So we can use the knowledge of Lie group theory on the action of subgroups on the sphere or on other objects. In fact, we can study a lot of different notions of controllability, finer than the ones that I presented on my previous slide, to give a very good description of the controllability properties of the finite-dimensional group in terms of the Lie algebra generated by the Hamiltonians H naught HK. So this is a very first kind of result. In fact, as Gunther said, it dates back to works by Djurjevic, Sussman, Brocket, is that if SUN is contained in this Lie algebra, which I just mentioned, generated by the admissible Hamiltonians, then we have exact controllability of this system, because in fact we have exact controllability at least in SUN and sometimes in the group, and then we project down of course the action of SUN on the unit sphere is transitive. And then there is a more recent result, is again use the geometry of actions of groups of UN on the sphere, which says that as soon as we have approximate controllability in finite-dimensional system, in fact, we have exact controllability. So the picture is quite, I mean, there is no much freedom between approximate and exact controllability in finite dimension. But I don't want to enter in this result. I want to stay in infinite dimension. So I just make a little switch in notations not to carry the I everywhere. So I just call A the operator H naught multiplied by minus I, and the same for the control operators. And I just a bounded neighborhood of the origin. So I assume that I call one of the admissible controls the origin, and I assume that I have a neighborhood of controls just around. And then, so this is just the same system rewritten in this notation. I have my complex Hilbert space, which I assume to be infinite dimensional, and I have the drift operator, which corresponds to A naught. So I have my first assumption, which can be slightly relaxed, in the sense we can just concentrate on the discrete part of the spectrum of A. But for this talk, I would like just to assume that the H, so in fact the Hamiltonian H naught is a discrete spectrum. So I call lambda n the eigenvalues, and phi n the eigenvectors, which form an orthonormal basis. I allow some eigenvalues to be equal, but in this case, of course, I should repeat lambda n and take more eigenvectors to span the entire space. And then I have some minimal regularity assumption on the controllable Hamiltonian, because since we have here infinite bounded operators, we have to be sure that we can give a meaning to the sum to start, to the sum of these operators weighted by some control UK. So the first regularity, if we want, assumption is that at least this BK are well defined, so the control operator are well defined on the eigenvectors of A. So this can be seen some kind of smallness of BK with respect to A in Kato sense. And it's less than that, but we go in that direction. Also here, with some Kato smallness of the BK with respect to A, we can define the sum of A plus these controlled operators and give a meaning to solutions of this system. And so this, the only really restrictive assumption here is this the discreteness of the spectrum of the Hamiltonian H0. And so we have we keep in mind some examples, interesting examples of Hamiltonians of this kind. So we can have the Laplace operator of compact manifolds, like for instance S1 or S2 when we try to control the rotational degree of freedom of a molecules, for instance. And we can have in mind the potential well example where the Hamiltonian is some Laplacian on some bounded domain with zero boundary conditions. So in fact, it's kind of infinite potential outside subbounded set, some bounded set, or we can have some coercive condition on the potential, so more as approximated example of potential V, which is summed to the Laplace in some some infinite space, sorry, Rn, for instance. Okay, this is the one appearing for Vx equal to x squared for the harmonic oscillator. So, as I said, we need this minimal regularity of the control operators to give a meaning to solutions. So in fact, we take solution controls which are admissible in the sense that they induce well-defined solution. And this, in this minimal setting that I already presented, is always true, at least for piecewise constant controls. And moreover, we want to have some stability of solutions with respect to the controls. We don't want to have so this is again some condition of which can be imposed as I recall here with some kind of Kato smallness. So the behavior of the controlled part should not be wild with respect to the uncontrolled. So we have to have some continuity of the trajectories with respect to u. So if we have a sequence of controls converging to some control u in L1, so in quite a weak sense, we want the trajectory to. This is just to say that there is some intuition in what happens if we perturb a little bit the control. We don't want too great perturbation in the trajectory. And so I will work always in this. With a class of admissible controls. If not, so I recall, just because I will mention in the next slide the existing result in literature, what I mean by exact controllability in some subspace of my Hilbert space H0 is that for every initial and final condition which are in a unit sphere and in this subspace, I have a control which leaves my trajectory all the time in this special subspace, and goes from psi0 to psi1. Approximate controllability we have already seen, so we want just to go close to the final state psi1 in the norm of the Hilbert space. And to have exact controllability in projection, I introduced this orthogonal projection on the first modes. Sorry. And exact controllability in projections is to say that for any initial state psi0 and any final state psi1, and for any n such that, okay, I don't want a psi1 to be completely contained in this space generated by the first n eigenvectors. If not, I would have exact controllability in some sense, which I will show that this is not possible to obtain in general. So I need some freedom, the fact that there is some reminder of population in the higher energy level. And with this tolerance which I give me, I know that so if I have exact controllability in projections, then there is an admissible control steering psi0 to some state, which is this flow associated to u up to the time t applied to psi0, which projects in the first n components exactly to the first n components of psi1. So to have in mind an example where to understand what the result says with respect to possible applications is we can try to encode in my infinite dimensional system some kind of random number generation in basis 10, for instance. So I take a prepared initial condition psi0, and then I say that if the system is exactly controllable in projection, I can send it to something like 1/10 phi1 plus 1/10 phi9 plus some phi reminder with the projection on the first 9 modes of phi reminder equal to 0. Okay, and then I can I know that I can do this exactly, so I can just measure in which level I am and obtain a digit which I can use to, I mean, a number between 1 and 10, 0 and 9, and create a number. And what I know, what the result, the exact controllability in projection tells me is that if I want to do this by taking a tolerance, so I want to implement this with a tolerance which is decreasing, so going to 0, then the time of the actual solution and the energy of the actual solution to, for instance, the L2 norm of U will stabilize in some sense. So I will not require more and more stronger and controls with longer time, which will become more and more unlikely, unsuitable for using. But in fact, I will just pay in terms of computational accuracy. But this is something which I cannot do anything for that. But I mean, there is no physical bound to which says that asking for a better tolerance gives a worse result in terms of control quality. In fact, the control have the same structure in all the neighborhood of the desired final condition. Okay, so let me give some previous results on controllability to introduce a little bit the general result that I will give in a couple of slides. We as Gunther said, in general, in infinite dimension, we cannot expect exact controllability. And in fact, this in this setting is related to some functional analysis constraints, which say that the reachable set from a given initial condition psi naught will not be equal to the entire sphere in the Hilbert space S. So this is based on remarks given in more general setting by Ball, Marsden, and Slamrod, and applied to the quantum setting by Turinici. And this is at least for the bounded control operators, and recently extended into the case of unbounded control operators, but with some smallness by Boussaïd, Chambrion, and Caponigro. And then we have some other results on specific cases, like the fact that the quantum harmonic oscillator is not controllable, not even in approximate sense, even if Galerkin approximations are controllable. I will come back to this later, because we use some, for our test for approximate controllability, some modification of a Galerkin approximation, and I will show why, at which moment this test fails to hold for the quantum oscillator. And then we have positive results on specific cases, like potential well examples by a series of papers by Karim Boshar and collaborators, and also for more general cases, both by Lyapunov techniques, adiabatic evolution, and for a series of papers, also by people in the room, on which use the structure of how the controlled operator behave with respect to the basis of eigenvectors of the operator A, which is in the spirit of what in fact, I will present as our result. Okay, so the result that I present is, first I will give it in the form of an approximate controllability result, and then I will go to the exact controllability in projections. And this approximate controllability result is, so I present the last of a series of results that we obtained in the last years, which are based on a similar scheme to give to check the controllability of the system, and also to construct, in fact, some controls which leads to approximate controllability. We should study the decoupling of between the infinite dimensional dynamics and some finite dimensional dynamics, which we can identify, and we can on the infinite dimensional system with arbitrary precision. And for this, we should use some convexification scheme at the infinite dimensional in the infinite dimensional space. And then once we identify these finite dimensional motions which we can generate, then we just use a finite dimensional result of controllability to combine them to obtain the desired goal. So in fact, what we do is some simultaneous control at the finite dimensional level, and of this unwanted transfer of population to the higher energy levels. And so what I want to say in this slide is that already starting from the first of these results, this was enough, even if it's less general than the one I will present, to prove that in fact what I mentioned in my first slide, that generically these systems are controllable. So we can take, for instance, a Schrödinger equation like this in Rn, and say that for a generic choice of W, let's say, so I take W in, for instance, in L infinity, and for a residual set in L infinity, so in intersection of countably many open and dense subsets of L infinity, whatever is V, I will have a controllability. This typical example of what we can prove in this setting. Okay, so to formulate our test for controllability, I need some notations. So first I take any n times n matrix with complex entries, and I fix a sigma here, and this I see that spectral gap, and I want to excite the matrix at this spectral gap. What it means that I just keep those elements of the matrix which corresponds to indices Lj, which have a spectral gap. So these are the eigenvalues of A. I remember I always use this notation. So I check if this spectral gap corresponding to the indices L and J is equal to sigma. If it is, so this is the delta Kronecker. If it is, I keep my element MLJ as it is. And if it's not, I put a 0. So if, for instance, I take a sigma which is different from any spectral gap of the system, then this operation just gives me a 0. And then what I do, in fact, I look at, so these are my operators, Bj and A. I introduce this notation to say that I just want to crop. When I put an n over there, like in parentheses, I crop, I take the operator B, which I see as an infinite dimensional matrix, and I crop the first n times n entries. Okay, this is B. So A is diagonal, so I prefer to make the example with B. And then this one will be my BKN. And if capital N is larger than small n, then I will crop something larger like this. And then I will select these pairs sigma and k. So sigma is a spectral gap, and k is one of the indices of the controls. So is this j here, such that when I do this operation with, so I have my small n which is fixed, and I take a capital N larger and larger, and I want that every time that I do this crop with n large, I get just 0 here. All this should be 0. In fact, I could do the crop, the infinite dimensional crop already of the first small n lines. This is my condition, and this says that this matrix here is something which I can use, I can mimic with my infinite dimensional system. So it will give some finite dimensional dynamics that I can mimic with the infinite dimensional system. And then I collect all these dynamics. So I take the one, so this is again at a small n which is fixed. I take all this this possible dynamics. So this okay, are at most, in fact, I can use I can have one of these for every k and for every spectral gap sigma, and the only one for which I have something different from 0 are the spectral gaps corresponding to indices between L and J. I can also look at the others one, but I will, as I said before, I just obtain 0, and so no useful dynamics to use at the n dimensional, at the n level. So this will be will define my adapted Galerkin approximation. And so the general result I was mentioning is that if I don't ask that for every n I have controllability of this adapted Galerkin approximation, but at least that I have infinitely many of these Galerkin approximations that are controllable, and this is useful, in fact, to make this difference in the examples that I will present just right away. So the first example is this potential well, this model studied by Karim Bochar and collaborators that I mentioned before. So we have a one-dimensional subset of R, so an interval, and then we have a Laplacian with no further potential, and then we have a control potential which is x. In this case, everything is explicit for what concerns the operators A and B. We can compute the eigenvalues, they are well known, the eigenvectors of A, and then also the elements of B. What is important is what are the elements of B which are different from 0. And in fact, this is any two diagonal, we have elements which are different from 0. And what it's not hard to say is that all these matrices here, so the only one which are interesting are the one which correspond to spectral gaps which are given by subsequent eigenvalues. And in this case, they decouple well, so we have really all these zeros that we wanted, and we can collect this, which are matrices which will have an element different from 0 here by construction in the upper diagonal, and maybe some other elements which will not disturb us in the computation of the Lie algebra. In fact, for every n, we have that the Lie algebra generated by this contains SUN, and so in fact we have controllability at any n, and we recover this approximate controllability result in this setting, not the full exact controllability in spaces of the type H3, but at least approximate controllability. Okay, another example which I promised you is the quantum oscillator. In this case, we know that the system is not approximately controllable, so we expect our test to fail, and then we check why it fails. So in this case, again, we can compute explicitly A and B, and in fact B is 3-diagonal. And what is important is that if we take the spectral gap equal to 1, which corresponds exactly to the upper and lower diagonal, we have always an element here. So in the place we don't want it to be, because it will say that this crop there is never equal to 0 for the spectral gap equal to 1. So we cannot collect matrices corresponding to spectral gap equal to 1. And for all other spectral gaps, in fact, we find a 0 here. So it's not interesting neither. So in fact, we don't have enough matrices to conclude by our test, which is good, because if not, our test would be wrong. And then the other important thing is that our adapted Galerkin, so in this case, is just becomes just psi dot equal to an. So we just have the diagonal term, the uncontrolled system, which is not controllable. And it is different from the Galerkin approximation. The Galerkin approximation, actually, it is controllable. So in this case, we have much less freedom in the admissible, inadapted Galerkin approximation than in the full Galerkin approximation. Okay, and this is the other example where it's important to have this fact that we just ask to control infinitely many adapted Galerkin approximation and not all of them, because it's an example where we have spectral degeneracies which are quite strong because we have eigenspaces which can become of arbitrarily large dimension. It is an example with a drift term which is a Laplacian, in fact, on a compact manifold. In this case, the compact manifold is S2. So this is a model for rotation with two angular degree of freedom, which are here theta and phi. We have three controls which correspond to three fields which are not collinear, because if not, we will have too many symmetries to control the system. And in this case, again, we can do the computation. That's to say that this test, at least for a system which can be described analytically, it's a test which requires a little bit of computation, but even if it's an infinite test in the sense that it asks infinitely many Galerkin approximations to be applied. It can be done on the paper on systems which are possible to describe analytically. Okay, and then there is another example to say that it not only applies to cases where we can compute completely the operators A and B, in the sense to really write what is the value of the entries of B and A. And for this case, so I take a model for an interaction between a bosonic and a spin state. And so here is the drift Hamiltonian. So we have the quantum oscillator on this infinite dimensional component L2, and just two-dimensional component C2. And then we have an interaction term given by some parameter G. And we assume some form of resonance between the frequencies omegas, and then we have a control which acts on the bosonic state like as in the quantum oscillator. And in this case, what we can compute are what happens at G equal to 0. So it's the situation where we have decoupling in the Rabi Hamiltonian there, but by using all this information, also the derivative with respect to G of the Hamiltonians at G equal to 0, and using analytic properties of the system, we can say that this test for controllability actually works for almost all G in R. Okay, so now I go to the last part of my talk, which is about really about exact controllability in projections. So the hypotheses here are exactly the same as before. So I don't change anything. So again I ask that for infinitely many n, small n, the adapted Galerkin approximation is controllable in the sense that this adapted dynamics in dimension n obtained by this crop there are generate the Lie algebra, generate the entire SUN. And then in this case I have, so in all the examples that I presented up now, I have this exact controllability in projections. And I can be more precise of which controls I can use to get this controllability projection. So as I said, under my standing assumptions, piecewise constant controls are always admissible. Then I can get exact controllability projections using piecewise constant controls. And as soon as moot controls are admissible in the sense that I presented before, then again I can get exact controllability projection with these controls, and I could extend the result to some form of exact operator controllability in projections, where again I should ask. So again I do an operator controllability, but I just test the value of the operators on a finite, albeit arbitrarily large number of eigenvector phi j, and I should ask that all of these phi j's that I want to control exactly in projections are not sent again to the span of this first n eigenvalue. So I can prolong a little bit this exact controllability in projection to controllability for operators or density matrices. I already gave some idea of how I do the decoupling, but I will give some more detail analytically in the next slide. But how now I combine the approximate controllability with exact controllability in projections. So the idea is the following. I take a small n there, for which I have approximate controllability, and I take a final state for which I I have this tolerance. I mean, I have this the fact that psi1 is not contained in the span of the first n eigenvectors. And then I know that this is different from 0, so I have this tolerance which I call epsilon, something in between this value and 0. And then for every phi which is in the epsilon neighborhood of this projection that I want to achieve, I first lift phi to some element phi hat which is in the infinite dimensional space and projects down exactly to phi. Okay? So for every element phi, I do this projection. And since I know approximate controllability, I can also select a control which depends on this u phi and also will depend in general of this lift here, which gives a approximate controllability towards this the projection of this psi1. So this is here. So u phi is steering psi0 to a neighborhood of this element which I lifted. Okay, and now what I do, I look at this operation which associates to phi the control u phi, and then I project down to psi(n). So I know that here I don't obtain exactly phi hat, but I am in a neighborhood of it. So in fact I have this operation which is continuous with respect to phi, and which is close to the operation which is the identity, which projects phi to which sends phi to itself, and for which in the image there is the state that I want to obtain, this psi(n) of psi1, Pn of psi1. So I conclude by standard degree, topological degree arguments, which are very, I think, can be easily understood on this picture. So I just say that if I have a map which is defined on an open and bounded set X, which is in red here, and if I have a map there which is close to the identity, then any point y0 which is far enough from the boundary, so this epsilon is the distance from the boundary, which is larger than this difference from G to the identity, then x0 is in the image of G. And this is what I want to obtain, because for me, y0 will be exactly this projection that I want to get, this Pn of psi1. I have my G will be this map here, which is close to the identity because I have this approximate controllability there. So as soon I can construct this u phi in a continuous way with respect to phi, then I am done. So I have to combine this approximate controllability that I know to hold with some construction which is continuous with respect to phi. Okay. So to see that this construction is can be done continuously, then I use some the key point is to say that this decoupling between finite and infinite dimensional directions is obtained by a construction which is a repetition of some periodic control, which is defined in some canonical way, and so which does not depend on the final state phi. And so maybe I will not enter in the details of this one, but okay, this is just to say that combining this with some notions of normal controllability which come from geometric control theory, I can be sure that in fact I cover a neighborhood of the state that I want to obtain, and I conclude by topological degree theory, and I'm done.